Welcome to this first lecture on matrices. A matrix is a rectangular array of numbers in rows and columns and enclosed within brackets or parentheses. So, if we have the following numbers, say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. And you observe that these numbers are arranged in such a way that the numbers 1, 2, 3, 4 are on the same row, which I shall call row 1. 5, 6, 7, 8 are on the same row, I call row 2. 9, 10, 11, 12 on the same row, row 3. Likewise, 13, 14, 15, and 16 on the same row, which I call row 4. So row is from my left to the right. And then 1, 5, 9, and 13 are on the same column, which I call column 1. 2, 6, 10, 14, I call column 2. 3, 7, 11, and 15, I call column 3. And then likewise, I call this part here column 4. So we observe that these numbers are arranged in a pattern such that some numbers are on the same row while others are on the same column. If we have such an arrangement of numbers or element or whatever it could be, and if these numbers are enclosed within brackets or parentheses like this, then this arrangement will be called a matrix. So this would mean that my matrix here has 1, 2, 3, 4 rows and 1, 2, 3, 4 and 4 columns. So I could denote this matrix, using a capital letter, say A. So A equal to the matrix with entries or elements 1, 2, 3, 4, 5, 6, 7, 8 up to 16, such that there are 4 rows and there are 4 columns of the matrix. So these guys inside here are what we refer to as the elements of the matrix, or the entries of the matrix. So I shall be using more of the word entries. So once you have an arrangement of numbers in this pattern, then what you have is a matrix. So we shall be studying such kind of system and their properties. More generally, I could write a matrix A equal to A11, A12 up to A1n, A21, A22 up to A2n. I can continue up to AN1, AM1, AM2 up to AMN. Now if I write this would mean the general form of a matrix. Here the first entry is A11. I bring it out here, A11. We'll talk about it in a moment. This is a matrix with how many rows and how many columns. Let's see. This is row 1. This is row 2. This dot means that the rows go on and on. So the rows go on until the last row is row M. Then this is column 1, column 2, column 3, column M, column N. So this matrix has M rows and N columns, while the matrix here has 4 rows and 4 columns. But here, we're not specifying a general matrix. And the subscript we have here on A, or on each of these entries, has a meaning. This entry A11 in matrix notation would mean that A is the entry of the matrix that occupies row I and column J. So A11 means the entry in column I, in row I and column J, where the first subscript here denotes the row of the entry A, and the second subscript here, 1, denotes the column of the entry A. So this other one, this second entry, A12, would mean that this entry A is in the first row, row 1, and the second column. And that's true. A12 is in the first row and second column. We can go on and on. The last entry here, A1n would mean the entry in the first row and the nth column. So If we relate the notation to what we have for our first matrix A, this entry here, 11, would be what in terms of notation? This would be the entry. Let's see, this entry is in row 3 and column 3. So that entry would be A33. The entry in row 3 and column 3. Let's be one more entry. This entry 9. What would be its notation? This entry 9 is in row 3 and column 1. So entry 9 is entry A31. So there's an entry in row 3 and column 1. This will not be the same thing as writing A13. Because if you write what A13, this would mean the entry in row 1 and column 3. And that is not 9. So the entry in row 1 and column 3 would be row 1. This is row 1, column 3. This is the entry. That's the entry in row 1, column 3. So generally, we could represent a matrix as A equal to then Aij. So this means that this matrix A has entries Aij. Of course, where the I and the J specify the row position of the entry A and the column of the entry A. We shall dig more into this in a few seconds. Order of a matrix. This is a number of rows and columns of a matrix. Sometimes we call order of a matrix dimension of a matrix, though this means something deeper later on. So dimension of a matrix or order of a matrix. This simply means the number of rows and columns of a given matrix. For instance, let us go back to our very first candidate A. Now this matrix here is a matrix that has 4 rows and 4 columns. So this matrix is of order 4 by 4. Of order 4 by 4. Where the first 4 signifies the number of rows of matrix A, and the second 4 signifies the number of columns of matrix A. But in matrix notation, we wouldn't write 4 by 4. What we write is 4 times 4. So 4 with a little cross and then 4. So this simply means a 4 by 4 matrix. So this 4 by 4 is what we refer to as the order of the matrix or the dimension of the matrix. So if you're asked, what is the dimension of matrix A? You simply check how many rows has matrix A and how many columns. So it has 4 rows and 4 columns. Therefore, its order or dimension is 4 by 4. In writing, you write 4 times 4. Our second matrix here, which was a general matrix, also has a dimension. What would the dimension be, or the order? We check. This matrix had how many rows? 1, 2, up to m rows. So this matrix had m rows and how many columns? 1, 2, up to n columns. This matrix had m rows and n columns. Therefore, the order or dimension of our matrix is m by n. In writing, we write m times a little n. Now take note, we cannot write m by n as n by m, as this would mean something totally different. This would mean that our matrix has n number of rows and m number of columns. In other words, this order, is actually ordered in the sense that the first number you write here signifies the number of rows and not columns, and the second one signifies the number of columns. Let us take one more example. If we have a matrix, say matrix B, with the following entries, say 1, 2, 3, 4, 1, 0, say -1, 2, 3, say 4, 5, and 6. If we have the following matrix with these entries, and we are asked, what is the order or dimension of our matrix? What will it be? We simply check how many rows has a matrix first, then how many columns. So let's check. This is row 1. This is row 2. This is row 3. This is row 4. So this matrix has 4 rows. And how many columns? Column 1, column 2, column 3. We have 4 rows and 3 columns. Therefore, this matrix is matrix 4 by 3. Which is a wrong way of writing it. Instead, we'll write 4 times a little 3. 4 times 3. So this is matrix 4 by 3. So this completely specifies how many rows has our matrix and how many columns. So if I write matrix B as, I say matrix B is a 4 by 3 matrix. What that would mean is that my matrix has 4 rows and 3 columns. I hope it's clear. Now, there are times where one may not want to, write out all the entries of a matrix in this way, and instead, we write it out in a more compact form. For instance, if we say that matrix C is equal to the matrix with entries A, I, J, and is equal to I squared plus J. Now what you see here completely defines the entries of matrix C. Now from this definition of a matrix C is a matrix with entries A, I, J. Recall where I here refers to the column position of A and J refers to what? Sorry, I the row position and J the column what? Position. So all the entries of this matrix, whatever the order is, obeys the rule I squared plus J. What is I? Row squared plus J. J is the column. So with this definition of a matrix, we can construct a matrix of any order or dimension. For instance, we can construct a matrix from here, a matrix of order, let's say 3 by 3. And how would that look? A matrix of order 3 by 3 looks like this. A11, A12, A13, A21, A22, A23, A31, A32, A33. Why is this order 3? Let us see. Because it has 1, 2, 3 rows and 1, 2, 3 columns. So this is a matrix of order 3 by 3 or of dimension 3 by 3. So we can now check out what each of these entries of matrix C will be by the formula I squared plus J. So the first entry A11, let us see. A11. A11 simply means the entry in row 1 and column column 1. Row 1, column 1. So in that case, using our formula I squared plus J. I squared plus J. Where I here is the row position and J is the column position. So A11 is in row 1, column 1, right? So row 1 means I is 1 and column 1 means that J is 1. So if you substitute that here, we simply get row 1, I is 1 squared, J is also 1. So that 1 squared is 1 plus 1 and 1 plus 1 is 2. So what this means is that in our matrix here, C, the very first entry of our matrix is 2, since 2 is A11. So likewise, you can get the second entry, A12, as the entry in row 1 and column 2. So now our formula I squared plus J. I means number of row or the row position, which is row 1, J is column 2. So that becomes 1 squared plus 2. 1 squared again is 1 plus 2, and that is what? 3. So the second entry of matrix C is what? Is 3. The third entry, A13, again, I squared plus J, shall be I is now 1, J is 3. So 1 squared plus 3, and that will be 1 plus 3 equal to 4. The next entry here is 4. So we can go on and on to get the A21 entry, A22, A23, A31, A32, A33. Let us take one more. Let us check what the entry A32 will be. So A32 would mean the entry in what? In row 3 and column 2. So I now will be 3 and J will be 2. So that becomes 3 squared plus 2. Now 3 squared is 9 plus 2. So 9 plus 2 is what? Is 11. So the entry A32 will be here. So that entry is what? Is 11. So with this, we can get to know all the entries of matrix C. So with this simple formula here, we can generate the entries of a matrix of any order. So if you are told, for example, to use this to generate a matrix of order, say 10 by 6, 4 by 6, there's no problem. We just put them down like this, and then taking note of the fact that the first subscript here, defines the row of the entry A, and the second subscript defines the column number of the entry A. And with that, we can, so you fill this up, you check what these entries will be, and fill up matrix C. Now let's take some definitions, and of course types of matrices that we shall encounter throughout this course. The first one is what we call the row matrix, or sometimes we call it the row vector. This is a matrix with only one row and any number of columns. We call that a row matrix. For instance, matrix A is equal to the entries 1, 2, 3, 4 up to, let us say, n. Now, we claim that this matrix here is called a row matrix or a row vector. So this matrix has how many rows? Let's see. One row, just one row. And how many columns? 1, 2, 3, 4. It goes on and on up to column n. So this matrix is what dimension? Is 1 by n. It has one row and just an n number of columns. So we call this a row vector or a row matrix because it has just one row. So if a row matrix, if it has one row and two columns, it's a row matrix. If it has if it has one row and 5 columns, it's a row matrix. If it has one row and 100 columns, it's still a row matrix. What makes it row is the fact that it has just one row. So similarly, we have what we call a column matrix or vector. A column matrix, on the other hand, will be a matrix that has just one column and any number of rows. For instance, if matrix B is this, a matrix with the entries 2, -1, 3, it goes on and on up to n. Now, what's the dimension of this matrix or the order of the matrix? A matrix of how many rows? 1, 2, 3, up to row n, so n rows, so n by how many columns? 1 column. So this matrix has n number of rows and just 1 column. Since it has 1 column, we call this matrix a column matrix or a column vector. So if it has 5 rows and 1 column, it's a column vector. If it has 10 rows and 1 column, it's a column vector rather. So what makes it column vector is the fact that it has just 1 column. That is it. The next one I want to look at is what we call the square matrix. So a square matrix, this is a matrix with same number of rows and columns. For instance, if I have matrix A with the following entries 2, -1, 4, and 6. Now the dimension of this matrix or the order of the matrix is 2 by 2. The matrix has 2 rows and 2 columns. Since the number of rows and the number of columns are the same, matrix A is called a square matrix. So we say A is a square matrix of order what? Of order 2. Or of order 2. Since it's a square matrix, we can just say of order 2 instead of saying 2 by 2. Since it is 2 for the number of rows, it's the same 2 for the number of columns, we can just say of order 2. How will an order 3 square matrix look like? Let us see. So if B is a square matrix of order 3, it will look like this. Let us say 0, 1, -1, 2, 3, 4, 6, 8, 10. This would be a square matrix of what? Order 3. Since it has 3 rows, 1, 2, 3, and equally 3 columns, 1, 2, 3. That's a square matrix because it forms a square. It forms a square actually. So that is a square matrix of order 3. And of course, in the theory of matrices, square matrices are the most important or one of the most important types of matrices we shall be dealing with. So if a matrix has 3 rows and 4 columns, for instance, would that be a square matrix? The answer is no. Because for it to be a square matrix, the number of rows and number of columns must be exactly the same. So 3 by 3 would be a square matrix, 4 by 4 would be a square matrix, 5 by 5 would also be a square matrix, but 3 by 4 is not a square matrix. 4 by 3 is not what? A square matrix. And for a square matrix, the entries 0, 3, 6, these entries here, use red now to take them off. Those entries 0, 3, and 6, the entries from the top left corner of the matrix to the bottom right corner of the matrix have a special name. They are called the diagonal entries. Other times we call them the entries of the main diagonal, or sometimes we call it the principal diagonal. So these entries 0, 3, and 6 have a special name. They are called the diagonal entries, or the main diagonal entries, or the principal diagonal entries, and the other ones are just the off diagonals, what they call off diagonal entries. So these entries 0, 3, and 6, they play a very important role in the theory of matrices, as we shall see later on. Diagonal matrix. This is a square matrix whose non-diagonal entries are all zeros. Now we know what we mean by diagonal entries, right? So let us see one, how it look like. So if I have a matrix, say matrix A, with, let us say, a 3 by 3 square matrix, or a square matrix of order 3, with the entries 2, 0, 0, 0, 4, 0, 0, 0, say minus 1. Now this would be a square matrix of order 3, right? But you observe that in this square matrix, the diagonal entries are not zeros, or are all not zeros. Of course, 1 or 2 can be 0, 4 can be 0, or minus 1 can be 0, but they are all not zeros. But what happens? The entries of the other diagonals are all zeros. So only the entries of the diagonal, or the main diagonal, or principal diagonal are not all zeros. Every other diagonal, this diagonal is 0, every other diagonal is 0. So above these diagonal entries, you have zeros. Below the diagonal entries, you have zeros. So matrix A is called a diagonal matrix, or a diagonal square matrix of order 3. How will a diagonal matrix of order 2 look like? Let's see. Let's say minus 1, 0, 0, 0. It's an example, because the principal diagonal entries, or the diagonal entries here, are all not zeros, because this is not 0. Even though this one is 0, there's no problem. But what happens is that, aside from these diagonal entries, every other entry of a matrix is a 0 entry. So we call this kind of matrix a diagonal matrix. Identity or unit matrix. This is a diagonal matrix having 1s on the diagonal and 0s elsewhere. So the first thing here is that an identity matrix or unit matrix is first a diagonal matrix. And we know what diagonal matrix is. A diagonal matrix is a matrix that has entries, that its diagonal entries are all not zeros and zeros elsewhere. So a unit matrix is also a diagonal matrix, but this time around, the diagonal entries or elements are strictly 1s. For instance, if we have a matrix, say matrix D, a 3 by 3 square matrix, we have entries 1, 0, 0, 0, 1, 0, 0, 0, 1. Question is this matrix D a diagonal matrix? The answer is yes, it is, because the diagonal entries are all not zeros and other entries are zeros. So this matrix is a diagonal matrix. Now the next question is this matrix also a unit matrix, or what we call identity matrix? The answer again is yes. So for a diagonal matrix to be called a unit matrix or an identity matrix, the diagonal entries must all be 1 and other entries must be zeros. So this is a unit matrix. And of course, this is a unit matrix of order 3. So we'll write as capital I with a subscript 3. So once we see this going forward, this simply means a unit matrix of order 3. That means a 3 by 3, square unit matrix. What happens if one of these entries here is 0? Take for example, this one here is 0. Would this still be a unit matrix? The answer is no. But would this still be a diagonal matrix? The answer is yes. So this will now be a diagonal matrix of order 3, but not a unit matrix of order 3. In other words, to be called a unit matrix of order 3, all the entries of the diagonal, main diagonal or principal diagonal, must all be 1s. So let us see how a diagonal matrix or a unit matrix. Okay, let us see what will I2. Let us say I4. Oh, how will I4 look? It look like this: 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 0, 1. So this is a diagonal matrix. See, the diagonal elements or entries are all 1s, and elsewhere we have zeros. So this is a diagonal matrix, and not just that, this is an identity matrix of order 4. So we have order 5, order 6, and order 7, and in fact order n. And this matrix you see here, the unit matrix, plays an important role, very important role in the theory of matrices. All these we shall see in subsequent lectures. The next, upper triangular matrix. A square matrix A, so it must be a square matrix first. A is called upper triangular if all entries below the diagonal are zeros. So let us see how it looks like. We have a matrix, say matrix E, as let us take a square matrix of order 3 with the entries 2, 1, 3, 0, 3, 6, 0, then 0, 0, 4. Now the claim is that this matrix E is an upper triangular matrix. What does it mean? Let's see. Now where are the entries of the diagonal? See them here. 2, 3, and 4. These are the diagonal entries, 2, 3, and 4. What do you observe? You observe that below the diagonal entries, all other entries are zeros. There are 3 zeros here, 1, 2, 3. And these 3 entries are below the diagonal entries. Are you there? So this matrix is called an upper triangular matrix because it forms a triangle to the right or up. Hence the name, upper triangular matrix. So an upper triangular matrix is a matrix whose entries below the diagonal are all zeros. So here we could have zeros in many places, but not everywhere. Like we have 0 here, there's no problem. But the major thing here is that the diagonal entries, shall all not be zeros. Below the diagonal entries, we have zeros everywhere. Upper triangular matrix. So a lower triangular matrix will be a matrix in the reverse order. So for a lower triangular matrix, we shall have that all the entries above, the diagonal entries are zeros. For instance, if this matrix, say matrix F, is now, say, 2, 0, 0, 1, 4, 0, let's say 2, 1, and 6. So what happens here? The diagonal element entries are 2, 4, 6. And what happens? Above the diagonal entries, every other entry is 0, 0, 0, 0. If one of these entries is not 0, let's see if this one is 1, it fails to be a lower triangular matrix. So all the entries below the diagonal, above the diagonal rather, are zeros. So this forms a triangle at the bottom of the matrix. So this is what we call a lower triangular matrix. This matrices once again plays a very important role when we try to solve a system of linear equations, as we shall see later. What is the transpose of a matrix? The transpose of a matrix A, written as this, A raised to the power T, is the matrix obtained by interchanging corresponding rows and columns. The keyword there is corresponding. I'll explain this as an example. Very simple. If I have a matrix, say matrix A, it mustn't be a square matrix, take note, with entries 1, 2, 3, 4, 5, 6, 1, 2, say 0. In fact, let me use something that's not square. Negative 1, 2, and 3. Now, this matrix is of what order or dimension? Let us see. 1, 2, 3, 4 rows, and how many columns? 1, 2, 3 columns. So this is a 4 by 3 matrix. It's not a square matrix. Now, there's another matrix called the transpose of matrix A, denoted as that, A raised to the power T. Now, this matrix is a matrix obtained from matrix A by interchanging corresponding rows and columns. Now, what does that mean? It means that in our new matrix, which is going to be the transpose of matrix A, column 1, row 1 of matrix A becomes column 1 of matrix A transpose. Row 2 of matrix A becomes column 2 of matrix A transpose. Row 3 of matrix A becomes column 3 of matrix A transpose. And row 4 of matrix A becomes column 4 of matrix A transpose. What does that mean? Let's see. So A transpose would be, A has row 1 as 1, 2, 3. For the transpose matrix, 1, 2, 3, instead of being row 1 becomes column 1. 1, 2, and 3. We go back to the first matrix A. Row 2 is 4, 5, 6. Now, in the transpose of the matrix, 4, 5, 6 becomes column 2. 4, 5, and 6. 1, 2, 0, which is row 3, becomes column 3 here. 1, 2, 0. And negative 1, 2, and 3 of row 3 of matrix 3 becomes column 4 rather. Row 4 of matrix A becomes column 4 of the A transpose. So negative 1, 2, and 3 becomes negative 1, 2, and 3. What then is the order of the transpose? Let's see. 4, 1 rather, 2, 3. 3 rows, 3 by how many columns? 1, 2, 3, 4. 4 columns. So matrix A is a 4 by 3 matrix, while the transpose is a 3 by 4 matrix. And this is obvious because we have swapped the number of rows to become the number of columns. So if matrix A has 1, 2, 3, 4 rows, its transpose will have what? 4 columns. And if A has 3 columns, the transpose will have what? 3 rows. I guess that's easy enough. Let's just take one more example, very quick one. Matrix B has the entries 1, 2, 3, 4, 1, 3. This is what? 1, 2, this is a 4. This is a 2 by 1, 2, 1, 2, 3, 2 by 3 matrix. So we want to obtain a transpose of that matrix. So transpose of matrix B. So we can even ahead of time. Okay, this one has matrix B has 2 rows and 3 columns. So the transpose will have 3 rows and 2 columns. Let's see if that's true. So row 1 is 1, 2, 3. That becomes column 1 of the transpose. So that becomes 1, 2, 3. Row 2 of matrix B, 4, 1, 3, becomes column 2 of the transpose. So 4, 1, 3. And that's the transpose. So what's the dimension of the transpose? 1, 2, 3 rows, 3 by how many columns? 1, 2, 2 columns. So matrix B is a 2 by 3 matrix, and the transpose is a 3 by 2 what? Matrix. Is that what we mean by the transpose of a matrix? Now that we know what the transpose of a matrix is, let us now know what is called a symmetric matrix. A square matrix A, it has to be square, take note of that. A is called symmetric if A transpose is equal to A. So what does this mean? This means that a matrix will be called symmetric if you transpose the matrix and the new matrix is the same as matrix A. Let's see an example. If I have a matrix, say matrix A with the entries 2, 1, 6, 1, 3, negative 2. So here is 6, negative 2, and 4. Let us get the transpose of our matrix. Now we know how to get transpose, right? So A transpose is what? Is a matrix obtained by interchanging what? Corresponding rows and columns. Very good. So in our transpose, row 1 of matrix A becomes column 1 of A transpose. So row 1 is 2, 1, 6. That becomes column 1 here, 2, 1, 6. Row 2 is 1, 3, and negative 2. That becomes column 2 of our transpose, 1, 3, and negative 2. Row 3 is 6, negative 2, and 4. That becomes column 3 of our new matrix, which is 6, negative 2, and 4. So what are the observations? Row A, rather matrix A, is 1, 2, 3. It's a 3 by 3 square matrix. The transpose is what? 1, 2, 3. The transpose again is a 3 by 3 square matrix. That's the first observation. What other observation do we have? Let's see. Matrix A has row 1 as 2, 1, 6. The transpose has row 1 as 2, 1, 6. The same. Matrix A has row 2 as 1, 3, and negative 2. The transpose has 1, 3, negative 2. Same as that of A. One last observation. Matrix A has its last row as 6, minus 2, and 4. And the transpose has the same rows, 6, minus 2, and 4. Wow. So what happens? So you see clearly here that the transpose of matrix A is the same as matrix A. Wonderful. This makes matrix A a symmetric matrix. So a matrix is symmetric if after transposing the matrix, you do not get a different matrix. You get the same matrix. Symmetric. Very important kind of matrix. Another type here called skew symmetric matrix. A square matrix, once again, is square. Is called skew symmetric if A transpose is equal to negative A. What does this mean? This simply means that transposing the matrix will be the same as multiplying every entry of the matrix by minus 1. Let us see how it looks like. For instance, matrix A has the entries 0, 4, negative 6, negative 4, 0, 3, 6, negative 3, and 0. So let's check out what the transpose of this matrix will be. And now you know how to get transpose, right? Yeah. So row 1, 0, 4, minus 6 becomes column 1, 0, 4, negative 6. Row 2, negative 4, 0, 3 becomes column 2, negative 4, 0, 3. And row 3, 6, negative 3, 0 becomes column 3, 6, negative 3, and 0. We close. That's a transpose. Now let us see what we observe. Now let's see what we would have gotten if we had multiplied each entry of matrix A by minus 1. Let's see. So that is a new matrix A. Let's see what it will be. So minus 1 times 0 would be 0. Minus 1 times 4 will be minus 4. Minus 1 times minus 6 will be 6. Minus 1 times minus 4 would be 4. Minus 1 times 0 would be 0. Minus 1 times 3 will be minus 3. Minus 1 times 6 will be minus 6. Minus 1 times minus 3 will be 3. Minus 1 times 0 would be 0. What do you see? You see that multiplying the entries of this matrix, each of them by minus 1, is the same as transposing the matrix. Do you observe that? Take a second to look at it. Yes, we multiplied each entry of matrix A, we got this, and what we have here is the same thing we got when we transposed matrix A. In other words, the transpose of matrix A is the same as multiplying matrix A by a negative number, minus 1. So when a matrix has this kind of property, such a matrix is called a skew symmetric matrix. Later on, we shall do something using skew symmetric matrix and a symmetric matrix. Let's take one more definition: trace of a matrix. This is the sum of the diagonal entries of a square, again, square matrix. For instance, if we have a matrix, say matrix A, a 2 by 2 matrix, square matrix with entries 2, 1, say 0, and 3. So what are the entries of the diagonal here? They are simply 2 and 3. You know what that is already. Entries 2 and 3. Those are the entries of the main diagonal, or just diagonal. And these entries, now to get the trace of this matrix A, which we denote as TR then of A. So this means the trace of matrix A will simply mean the sum of the diagonal elements. Diagonal elements are 2 and 3. So we sum them up. So 2 plus 3 is what? Is 5. So the trace of matrix A is 5. If we have a 3 by 3 matrix, square matrix, the same story. For example, matrix A is negative 1, 2, 1, 0, 1, say 3, 1, 3, say 4. We can also find the trace of matrix A. So the trace of matrix A is equal to the sum of the diagonal entries. So that is minus 1 plus 1 plus 4. So negative 1 plus 1 is 0. 0 plus 4 is 4. So the trace of matrix A is 4. We conclude by looking at addition and subtraction of matrices. Let A and B be two matrices of same order. That's a keyword, same order. The sum of A and B, written A plus B, is the matrix obtained by adding corresponding entries of matrix A and matrix B. So there's a condition here. Now before we can add or subtract matrices, the first condition is that they must be of the same order. What does that mean? It simply means that if matrix A, for instance, is a 2 by 2 square matrix, and matrix B is a 2 by 3 matrix, then matrix A cannot be added to matrix B. You can't add them. Why? Because matrix A and matrix B both have different dimensions or different orders. 2 by 2 and 2 by 3 cannot be added. And very soon you'll see why. So also, if matrix C is a 3 by 2 matrix and matrix D is a 2 by 3 matrix, they also cannot be added, because 3 by 2 simply means 3 rows and 2 columns, while 2 by 3 means 2 rows and 3 columns. These matrices cannot be added. So for you to attempt adding two matrices, the condition is that they must first of all be of the same order. Now when they are of the same order, how now do you add or subtract? You simply add or subtract corresponding entries of A and B. So let me illustrate an example, then we close. So we have matrix A is a matrix 2, 3, say negative 4, 1, 2, 3. Another matrix B here, very beautiful matrix, 1, 2, 3, 0, 1, and 4. So we want to now find out what is A plus B. I want to add the two matrices. So the first thing you must check out is, can A and B be added? How do you answer the question? You check out their orders or dimension. Matrix A is 1, 2, 1, 2, 3. Matrix A is a 2 by 3 matrix. It's not a square matrix. It mustn't be. Matrix B is what? 1, 2, 1, 2, 3. Matrix B is also a 2 by 3 matrix. So matrix A and B can be added. I hope it's clear now. Very good. Now that we can add the two matrices, how then do we add? We add corresponding entries. What does it mean? Now this entry here, 2, what is the position of this entry on matrix A? This entry is the entry that occupies what? Row 1 and column 1, right? Yes. This is A11. If you recall, this is A11. This entry is on row 1 and column 1. So what entry in matrix B is also occupying row 1 and column 1? Is this entry here, 1. So this entry is B11. It occupies row 1 and column 1 of matrix B. Therefore, the positions of these two matrices are what? Are equivalent. They have corresponding position. Just like saying, we have two families, A and B. The first son of family A and the first son of family B occupy corresponding positions, right? I hope you get it now. Very good. So back to A and B here. So 2, this entry 2 and this entry 1 are corresponding entries. So we can add them up. So we can add 2 and 1. I guess that. So again, 3 and 2 are corresponding entries because 3 here is in row 1 and column 2. And this entry 2 is also in row 1 and column 2. Corresponding entries. We put them also, we add them up into row 1 and column 2. So 3 plus 2. The last one is negative 4 is in row 1, column 3. 3 is in row 1, column 3. So I will add negative 4 and 3. I go on. This is in row 1. This is in row 2 rather, column 1. This also is in row 2, column 1. So I can add 1 and 0. This entry is in row 2 rather, and column 2. This entry is in row 2 and column 2. So I can add 2 and 1. This entry is in row 2, column 3. Entry is in row 2, column 3. I can add 3 plus 4. That is what we mean by adding corresponding entries. So if we do that, what do we get? We get 2 plus 1 is 3. 3 plus 2 is 5. Negative 4 plus 3 is negative 1. 1 plus 0 is 1. 2 plus 1 is 3. 3 plus 4 is 7. Beautiful 7. So what do you observe? This matrix also is a 2 by 3 matrix. So if we add a 2 by 3 matrix to a 2 by 3 matrix, the result we're going to have remains a 2 by 3 matrix. Now the same story we have for subtraction. If we say, let's do A minus B, same story. We'll subtract corresponding entries, just like we have added. So instead of doing 2 plus 1 corresponding entries, we'll simply do 2 minus 1. Since we are now subtracting, I hope it's clear. Next one will now be 3 minus 2 instead of 3 plus 2. This is for addition, this is for subtraction. The same rule. First of all, the matrices must be of the same order, and after satisfying that, you now do it, in terms of corresponding entries. The next one will be negative 4 minus 3, and now subtracting. Here will be 1 minus 0. Here will be 2 minus 1. Here will be 3 minus 4. And what would that be? Let's see. 2 minus 1 is 1. 3 minus 2 is 1. Negative 4, negative 3 is negative what? 7. 1 minus 0 is 1. 2 minus 1 is 1. 3 minus 4 is negative 1. And that again is a 2 by 3 matrix. So once again, when you subtract, two matrices of the same order, you get a third matrix of the same order. Let's see one counter example before we leave this place now. So if I have matrix A, for example, 2, 3, 1, 2, that's a 2 by 2 matrix, right? Good. It's a 2 by 2 matrix. And I have a second matrix, matrix B, with the following entries: 3, 1, 3, 2, 1, 2. So this is what dimension is 1, 2, 3. This is a 2 by 3 matrix. And you're now asked to add. I now say you should perform A plus B or A minus B. Question is, will this be possible? The answer is a resounding what? No. We cannot add these two matrices. Why? Simple. Matrix A is of dimension 2 by 2. Matrix B is of dimension 2 by 3. And a 2 by 2 matrix cannot be added to a 2 by 3 matrix because they are of different orders or dimension. How about A minus B? A minus B is also not possible because we cannot subtract two matrices of different orders. I hope you understand this first lesson. So please do not fail to leave a like on this video, share, and also please subscribe to my YouTube channel. Thank you, and see you in the next video. Bye-bye.